Okay, so we are back for the second set of questions, so that'll be questions 6 through 10. So remember that we're doing SIN 503, and that means if X happens in the experiment, then Y results will happen. So it's all about figuring out what conditions lead to like specific results, and that'll be given in the question. So number 6, a manufacturer has decided to produce armor plates using a ceramic material with areal density under 10. So let's find areal density in figure 3. That also offered the best possible protection. Based on figure 3, so that's where I'm told to go. Now, protection, if I'm using armor, right, I don't want it to penetrate, right? So I want the depth to be low. So protection here is going to be low DOP. So 10 centimeters under it. So this is about 10. So I need something with an areal density under 10 centimeters and the lowest DOP. So under 10 and the lowest DOP. So I'm going to highlight that particular line and figure out which material I should use here. So if I look at that particular line and then I look to the key, that's going to be B4C. So the answer to number 6 is B. All right, number 7. Based on the results of experiment 2, another research group has expressed interest in further testing the ceramic armor plate that exhibited the greatest DOP reduction. So, greatest DOP reduction. The research group would most be interested in ceramic armor plates with which of the following specifications? So, based on this result, thicknesses, DOP were plotted against areal density. Areal density is calculated by dividing the mass, blah, blah, blah. So, this research group would most likely be interested in. Now, I'm going to go over here. Which one of these has the most, or the biggest reduction? So, which one of those goes from the lowest DOP, because that's going to be low DOP, right? Means more protection, and the greatest DOP reduction, so we want small, so reduce, right, is going to be the same as decrease. So I highlighted this line. I'm going to go to my key. That's TIB2, and this is about this is between something and just under 17, so let's say 17 and 12, so that's going to give me the answer of D for 7. All right, I'll put that page this time. Number 8, using the same type of tungsten rod, another research group wished to conduct ceramic armor plate using a control DOP, so a control DOP of 2 centimeters. And I want the same type of tungsten rod, so that means it's going to be TIB2. So TIB2, and what would the control DOP of 2 be? So I'm going to go to my graph, and I'm going to find a DOP of 2 here. That's the control. And this research would most likely use. So, that means I'm actually going to go up to the second one, because if I look at my answer choices, the keys are launch velocity and then 2 and 4 centimeter thickness. So let's go here to launch velocity, a control of 2, and then this launch velocity, where are we? Where does that go down? So I went to 2, and then it brings me to launch velocity. It doesn't bring me to 2 thickness and 4 thickness, so I can cross off C and D because those aren't in the figures. Those are not the variables in the figures. Now here, this is between, let's see, 800, 900, 1,000, 1,100, 1,200, so that is between 800 and 1,000, so that means we're going to use A for 930, and that'll give us the answer to number 8. All right, number 9. Based on the data in figure 3 and the following procedure, so I'm going to use purple again because we can see, and the following procedure of experiment 2, which of the following actions would result in the greatest change of DOP? So figure 3 and following the procedure of experiment 2. All right, so a 15 by 15 armor mounted onto a steel wall, 65-gram tungsten rod was launched through the ceramic armor plate and into a steel wall. The DOP was measured. This was repeated with various compositions and thicknesses. The DOP values were plotted against areal density, divided the mass by the coverage area of the ceramic plate. So, if it has, so we did density, right? So this never changed, this 15 by 15 piece, and it's just the amount of volume that was covered. So that means if it has a higher density, it actually covered less of the plate. Now, what's the biggest change here? So when we're following this graph, replacing an AL2 plate with a TIB plate of the same areal density, and we're looking for the greatest change. So if I look at AL2, that's this solid line right here, and then with TIB2, that's down here, this change in DOP is about 4 to 1.5. So that's 4 minus 1.5 for answer choice A. B4C with SIC, so that's these two in the middle. B4C with SIC, let's see when they have the same in a straight line. The same in a straight line, I can cross off B because I know that's less. All right, replacing an SIC plate with a TIB2 plate, so that's SIC with TIB2. So that is going to be 1.5 and like 3.1. So I can cross off C. And D, B4C with an AL2. So B4C, this one here, and then AL2, that's about 4.5 minus, let's say 3.1. This one's still going to be bigger, so the answer is A. All right, number 10. Based on the data in the passage, which of the following changes would not result in the decrease in DOP? Replacing an AL2 plate with an SIC plate of the same size, that is a change. We can see that in the graph. Decreasing projectile velocity, so let's say we do this. We go that way. Does DOP change? Yes, it does. Decreasing the thickness of a TIB2 plate. So if I look at my TIB line, TIB2 here, does it say anything about thicknesses here? It says we tested them at different thicknesses. And then you see that. But we don't actually have that written, so we do not see the thickness results. And then D, affixing a ceramic armor plate to a previously unshielded steel wall. Now, if you put an armor plate on a steel wall but don't launch anything through it, you're not going to decrease the DOP, but you're not actually going to do the experiment either. So C is the answer choice that does the experiment. And that's the end of that particular exit ticket.